Let's go to our first fireside chat here at the event, and it's an absolute pleasure to introduce Amir Vaziri, Head of Customer Development at PhysicsX, and we're talking deep physics models, AI for the toughest problems in design and manufacturing. Amir, great to speak to you again. How are you?
I'm good, thank you very much. Thanks for inviting me to the show.
You're very, very welcome indeed. And as I was saying to the audience just a moment ago, we caught up yesterday. This is some fascinating stuff. So let's get into this because we've got a lot to cover. Let's go back for some company origins here. Let's get a bit of context here. Tell me a bit about PhysicsX, what it does, how the company got started. Paint us a picture.
Sure. So the company started around 5 years ago in motorsports. And, back then, AI was sort of like growing, and the company wanted to see how it can use AI to sort of accelerate design. And ever since then, our thinking around what AI can do for engineering has grown and matured substantially. And now we really want to change the way engineering is done across design, manufacturing, and operations to specifically improve product performance, accelerate time to market, and reduce product cost. And so where we're relevant across those three stages of the value chain are those CAE dependent or computer aided engineering workflows, the numerical simulations that are very time consuming. We're very relevant in those areas, and we want to infuse AI at scale across organizations, across these stages of the value chain to really achieve those values, which is, as I said, accelerated time to market, improved product performance, and reduced product cost.
What I really want to dig into, if I can quickly, is what the deep physics model is and how that differs from maybe more conventional approaches to AI that are currently used in design and manufacture. Can you break that down for me, please?
Yeah, so these deep physics models, they're really powerful models that can learn the relationship between a geometry and, your target variable or your surface fields very efficiently. Whereas in the past, some of the AI work that was done was more, let's say, on a parametric sort of view. So you would take a geometry, you parameterize it, and then you would have models learn on it. These deep physics models, because of their architecture, the way they're structured, they're so much more efficient at capturing as much of the data, as much of the information in data as possible, so that you would need much more fewer CAE runs to then optimize for your target metrics. And so what does that mean? That means that today in the world of engineering, let's say an engineer wants to optimize the design of a component, let's say, the aero, external aero of a car, or let's say like internal components, right? They will design that car, they will get the mesh, and then they will run this mesh in a time-consuming and an expensive simulation, right? And this could take hours, it could take days, and then the engineer will come back after a few hours and days and look at the performance of that specific geometry. What we can do is we can accelerate that time to 1 second. And therefore, the moment they generate their geometry, they can then quickly assess the performance of that specific geometry. We can then take this one step further, and we are able to generate practical and manufacturable geometries and then assess this in less than a second. And therefore, we can go about optimizing this whole component over the span of a few days rather than what it would have taken before. And so this is really the power of these deep physics models, that they can really capture as much nonlinearity and as much of the information as possible to enable these values for our customers.
The technology sounds phenomenally exciting, as I alluded to a moment ago. What I'd love to know is some examples about how this has worked in the real world. Now, of course, I'm sure there's a whole complicated web of NDAs that you can't go into. So if you don't name the company, I'm not going to push you for it. What kind of things have you seen in the real world? What sort of success stories?
Yeah, so we've worked with many clients, with many customers across multiple industries. So we've done work in auto, we've done work in aero and defense, in materials processing, in energy and renewables, in materials processing as well. And so the sort of work that we've done, for example, is for a car company, we optimize the performance of their cooling system, right? And so what we did is we brought our model and we trained it on a few CAE runs, and then we optimized the performance of that cooling system while reducing the development time. And at the moment, for a lot of our customers, this is significantly important. The speed to market, the time to market is one of those value levers that resonates with many customers. And so what we did is we built that workflow that optimized the performance of that component over multi-physics, right? So this was over thermal, this was over flow, and we could have also added some structural components to it as well. And so this is where these models really shine. They can do multi-physics in less than a second and really go about optimizing for that product end to end for all the target metrics that companies have in mind. We've also done work where we optimize the performance of a heart impeller, right? Again, a multi-physics problem. And what we wanted to do is we wanted to optimize the performance of that heart pump to reduce the energy consumption or improve the efficiency, right? While catering for the manufacturing constraints and also catering for other constraints, because this is blood. Blood is a tricky fluid. You can't pump it too hard. You can't pump it too slowly. All of these will cause complications. So we were able to produce that optimized geometry, which improved the performance, the energy performance of the heart pump by around 40%. And now it's actually the part that we designed, it got manufactured, and it's actually going through the trials at the moment. And I think this is also another important point which I want to highlight, which is around, for us, when we talk about better product performance or accelerate time to market or cheaper products, we want to see our customers realize that value. And what does that mean is we will go through this whole process, but we will provide a geometry that is manufacturable. We will take into account the manufacturing constraints that our customers have, because we don't want this to be just an exercise. We want this to be something that our customers can go print and realize the value or manufacture, like, they might have casting, it might be 3D printing, whatever it is, we will cater for that. So whatever they get, they can realize the values. And so the work that we do is not only in design, but we've also worked with our customers in manufacturing and in operations as well. And so the model that helps design something can be used to optimize, let's say, casting, right? If our customers are using casting as a manufacturing technique, we can then, improve their casting process. And then if the same component is being used in operation, we now have a model that produces predictions in less than a second. So then we can now use it in operations as well to realize value. So the value is across those three stages of the value chain.
What I'm fascinated to know, though, is we've spoken a lot about the customer experience, the speed, the experimentation you can do. Do customers ever come back to you, the engineers who you're working with, come back with unexpected benefits, things they didn't expect to find out? Because if they wanted to test out 1,000 different types of pressure, whatever, they could do that. It would take them months, years, who knows? But were there unexpected benefits they didn't expect to see, if that makes sense?
Yes. I think two examples here. One is when we were optimizing one of these multi-physics problems, which was for flow and structural. In fact, the optimization went on a path that wasn't expected by the engineers initially. And so, there was some skepticism initially, but then, once we let the model run and it really explored that space, they saw the merits of that. This was one of the cases where, we saw that there's another side benefit that we hadn't originally anticipated, and that is, it was sort of like a strategic move, which was, as I said, when we design components, we want to take into account the manufacturing constraints, right? And so these manufacturing constraints have a lot of implication on your design freedom, right? And so that design freedom also has a lot of implication on the performance that you will get out of that component. And so we worked with this customer. They were doing casting, and we produced a component, better performance. And then there was a question. They were like, but what if we sort of start relaxing some of those constraints? What would it mean? And we were like, yeah, but can you guys manufacture this? And they were like, we could assess this as a possibility for us to explore, other manufacturing techniques, such as, 3D printing. And so in essence, we then relaxed some of the constraints. We got much better performance. And then this will then allow our customers to then think strategically of, is it worth pursuing other manufacturing techniques to improve that product performance, to accelerate time to market, or reduce costs?
Where I want to go next, Amir, is about accuracy. Because obviously any question within the AI sphere, that there is that question about how accurate it can be. I put into ChatGPT whatever happened to Neil Perry, and apparently I died in a car crash in 2018, and there were tributes from across the media world. True story, bit scary, but we'll move on. Let's talk about the model accuracy here, though. How confident are we in the accuracy? What kind of feedback do you get from the engineers and the clients you work with? How does that work?
Yeah, a very, very good question, I would say. A lot of our people here are engineers, right? And you can train a model, and you can look at the performance of that model with your training data set because you have the ground truth, and you can optimize it. But then when you're doing real engineering work and this model then starts sort of extrapolating beyond what it's seen, it is important that what the model is predicting is close to reality, right? And we want to make sure that the engineers can sort of trust what these models sort of provide. And this is no black magic that we do. What we have embedded as part of our technology is we have accompanied our predictions with uncertainty quantification as well, right? So once the model is exploring areas very far from what it's been trained on, we also look at the uncertainty or the confidence that the model has in its predictions, right? And if that confidence is low, then we know that while the optimization led this sort of component to explore these sort of spaces, that we need to now surgically retrain our model in those areas where uncertainty is the highest. And this will allow us to then reduce the amount of simulation initially, to start an optimizer, see where the optimization takes us, and then surgically train the model in those areas of low confidence so that the model can then further explore and go about optimizing. And for us, this is very important because, if the model is not accurate, it can produce something, but is it, at the end of the day, when that part is getting validated, does it produce the performance that we wanted it? And so we have built, uncertainty quantification. We have also automated some of the workflows so that what happens is once the model identifies, areas where its uncertainty is the highest, it will automatically re-trigger training through the CAE. So this could be, your typical computer-aided engineering software that many companies use. And then it will take that training data and retrain itself, right? So we have automated that loop because that is also one of the levers by which we generate value, is the automation of this whole process.
I'm going to jump to questions from the audience now because they're talking about the building of trust and accuracy here. So let's go to Shabnam Gangar. Thank you, Shabnam, for your question. Shabnam's interested to know, how do you define and build trust within manufacturing and engineering industries by using AI to help achieve business growth?
Yeah, so the way we work is typically we start with a pilot project. We want that project to be a hard project on the critical path of customers, right? We want to be able to define that project and make it make sure that it contains the manufacturing constraints, things around the operating points, so that once we go through with this process, right, people at the end will be like, this is the technology we want to invest in. This is the technology that can change the way we do engineering, right? And so, on top of that, we are comprised of a multidisciplinary team. What that means is we have engineers in the team, we have data scientists, we have machine learning engineers. And what is important about this is, the engineers can speak the engineering language that our customers do, right? And then we can translate that to a data science problem and then go about solving it. So what that means is, by the end of that pilot, we have not only demonstrated the value of our technology, but we have also understood the challenges and the constraints of our engineers. And that's why time in and again, our feedback, one of the things we typically shine at is, the quality of our people, right? Our teams, we talk to our customers, we understand their challenges, we translate that challenge to a data science problem, and then we deliver the value. And so we say that, a lot of times we will work, success-based, and we say, if you don't deliver, it's fine, you don't have to pay us. So, all of these will make sure that when that finalized design is produced, customers will do a final CAE run. They will see that that component has achieved the results that we've said. We have built that relationship, and then we will work with them to build a roadmap on how we can scale this technology in their organization, because our thinking in terms of how we can deliver value is not about one simple, use case around, let's say, a heat exchanger or something. It's about having the platform that allows us to embed these models at scale and deploy and maintain these models at scale in our customers' organization.
I love how you sort of framed that about speaking the language of your customers. It's so important. If you don't understand them, how can you come up with a solution?
Absolutely.
More questions. They are coming in thick and fast, so I'm going to push through them if I can. Next one from James, who's an automotive engineering consultant. Thank you, James. How do you expect deep physics to transform engineering, and what's needed for this transformation to take place?
Yeah. So, deep physics, over time, these models will get smarter and smarter and better. And so they will radically enable engineers, right, to explore much further, much broader design spaces, right? And so, and this will allow companies to really be able to connect design to manufacturing and operations. At the moment, in many companies, these are siloed organizations. So someone from design will produce something, then will pass it on to manufacturing, and then pass it on to operations. But these deep physics models, because we can embed them, we can enrich them with real world data. So we not only take CAE data, but if our customers have real world data, we can enrich these models so their predictions go beyond the accuracy of CAE data. And now you have these deep physics models that are sort of providing, a ground truth for the designer and for the operations person and for the manufacturer, right? And so this is where that paradigm shift really happens, right? And I think this is the power of deep physics models, because these models need to be powerful enough for organizations, for companies to be able to realize this value, without having to do many CAE runs, without it, costing them too much, right? And so, and so this is really the power of this, and this is how we can transform organizations, engineer organizations, by connecting, breaking the silos and making sure that everyone has access to the same ground truth.
One last question for you, Amir, if I can. Questions have been coming in faster than I can get through them. Last one, quite specific. Are there applications of deep physics models for additive manufacturing? Is that
Absolutely. Absolutely. We've done a lot of work in additive manufacturing. This is anywhere from optimizing specific components of those 3D printing machines to working with the additive printing companies to optimize the tool path. In some cases, depending on the material, depending on the speed, depending on the structure of that component, there will be, there will be thermal effects that, for example, two layers won't attach, right? Or, there might be, once it's printed and cooled, there will be some deformations, right? We will work with the companies to build the technology so that it addresses those challenges. We have worked in additive. I mean, the cases are online. It's public. You can see it. We have worked with additive companies in the past. They also have it on their website. If you search PhysicsX and additive, I'm sure you will get some examples.
Fantastic stuff. As I said, there were more questions I could get through, but Amir, thank you so much for taking us through that. I did give you the big build up, told everyone it was fascinating, and it absolutely was.
Thank you.
We could carry on all afternoon, but I would get in trouble with the producers. Amir Vaziri from PhysicsX, thank you so much for joining us here at Manufacturing and Mobility Live.
Thanks for having me.
Absolute pleasure. Okay, let's crack on before I do get in trouble with the producers for overrunning.